Hello and welcome to my talk on building highly scalable real-time applications with AWS Appsync. This talk is based around a recent project that I worked on for a virtual events company. With COVID-19 causing a lot of in-person events to be cancelled and shifted online, this was a great opportunity for the client, but the increase in demand came with the challenge of scaling their application. It also came with the challenge that new competitors wanted to join the market, looking to take advantage of this same opportunity. And these competitors weren't held back by legacy code bases, existing clients, or old ways of doing things. They're able to utilize the newest technologies to build quickly and innovate. So the client decided they wanted to kick off a project to modernize their system, not just the look and feel, but also the underlying technology. And this couldn't be a 1 to 2 year complete rewrite with a big bang release at the end. They needed to be able to release quickly to make use of the opportunity. They also had an internal development team that needed to be trained on the newer technologies as their old system was written completely in .NET. So to do this, we decided to do a minimum viable migration. This is a strategy where you break down your existing system into a set of bounded contexts, and then you go through and you upgrade that system one piece at a time, releasing to production as you go. This allows the new parts of the system to piggyback on the old system, listening and events that have published from the old system to work in tandem. To find bounded context, we usually start with an event storming session, or since we use EventBridge, we do a variant called EventBridge storming. We decided a good first candidate for this would be the chat functionality. The existing version used polling to keep the conversation up to date. And not only is this an expensive approach at scale, it also doesn't give the best user experience. When we type out a message and click enter, we've come to expect instant feedback. We're no longer to wait a couple of seconds to see if our message sent. And with polling, you do have to wait for that polling interval to clear, normally a couple of seconds. We also didn't want to have to rewrite the entire front end just to upgrade the chat functionality. So we decided to use micro front ends to keep most of the existing front end in place and just replace the chat feature. So to recap, we decided we were going to replace chat first. It needed to support real-time updates. We needed to lower the cost, but we also wanted it to be able to handle that scale the platform was receiving due to the boom from COVID. The team to do this had about 4 weeks and consisted of 2 developers from Theodo, including myself, and 2 developers from the client side. A little bit about myself before we continue with the talk. My name is Alex White. I'm a cloud architect at Theodo. As you can probably tell, Theodo is a company that helps other companies deliver digital products, whether that's a startup working on an MVP or a more established company undergoing a digital transformation. When I'm not working with clients, I'm one of the editors of the weekly serverless transformation newsletter. Each week, myself and 2 colleagues, we sit down, we discuss our favorite serverless articles from that week, and then we pick our top 5 to send in the newsletter. I'm also the host and co-organizer of the Serverless London meetup, alongside 2 AWS serverless heroes, Ben Ellaby, who also works at Theodo, and Ant Stanley. Now the intro is out of the way, I just want to give a quick outline of the rest of the talk. So we've covered what the project was and its goals. Now we're going to look at what AWS Appsync is, starting with a high-level overview of GraphQL, and then focusing specifically on Appsync. And then we're going to link back to those original goals and see how Appsync allows us to have real-time updates, how Appsync will scale, and how training the team went. So first up, what is GraphQL? It's just another type of API. It's similar to REST or SOAP. It's made up of a specification and a runtime. Where it differs from REST is that it allows the clients to specify exactly what information it wants to receive. It also makes it very easy to join up multiple different data sources, and it has a type system to describe the data. The basis of any GraphQL API is the schema, and this is written in a schema definition language. The schema clearly defines the API in a very concise fashion, covers all the possible use cases a user could need, and is built based around types, with 2 high-level types, queries and mutations at the top. A query, like it sounds, is very similar to a GET request, and a post-mutation is very similar to a mutation is very similar to a post request. Here is a simplified version of a schema from the project that we've talked about. As you can see at the top, we define our query has a type query and mutation has a type mutation. If we look at queries first, you can see get user and get messages. Using get user as an example, you can see inside it takes a singular argument ID with type ID. Type ID is a built-in identifier type in GraphQL, and the exclamation at the end says that it's required. So we're saying that get user must have an ID sent with it. And at the end, you'll see that there's a user type. This is the return type of the query. So GraphQL supports both request validation and response validation. So the user can only send arguments defined here, in this case ID, but the server can also only respond fields in type user. This is very good for security reasons because it means that there's no way for people to get information they shouldn't have access to. If we now look at mutations and the send message mutation, we can see this has 2 required arguments and this time returns type message instead. Now it's been fairly high level, but it does cover the basics of GraphQL. Just to make it slightly clearer, here's an example. So with REST, if we wanted to get a user's information, we would probably hit a /user/ID endpoint, and that would just send back a predetermined list of fields, in this case, ID, first name, and last name. However, with GraphQL, you always hit the same endpoint, no matter what you're querying for, in this case, /GraphQL, but you can change that. And it would be a post request, and inside the body, you would define what query or mutation you're doing and what fields you would like to get back. So here we're sending get user with ID 1, and we want the first name and last name of that user. And so you'll see in the response, you get first name Alex, last name White. You don't get the ID. This is very useful. It links into my next slide about why you'd want to use GraphQL. First one is no more overfetching. So the client now only gets the fields requests and doesn't get a potentially large list of useless information. With this, particularly if you're working with slower internet speeds, say a mobile device out in the country, it provides a very good user experience. The other side is to prevent underfetching. So with underfetching, also known as the N+1 problem, let's use an example from chat. Say we want to get the last 50 messages, and when we do a request to get the last 50 messages, that returns a list or an array, and each item in that contains the message and a user ID of who sent it, because we want to display the username next to the message. We would then need to do a request for each of those users to get their username, since we only have the ID currently. Workaround for that with REST APIs is a strategy called backend for frontend, where you would actually write specific endpoints that just return the information that those front ends need. But this requires a lot more manpower, and it comes with a development overhead. With GraphQL, you get this feature out of the box. So the client can specify which fields it wants, and it only gets those fields. The next thing is it has a very good developer experience in general. Because the schema is tight, so you can generate TypeScript types through CodeGen. We normally use React on the front end, so it's very good at keeping our front end and back end types in sync. It also allows you to use tools like GraphQL, which support introspection, and those tools will automatically create Swagger-like docs for you. So that's a good intro to GraphQL. What about Appsync? Appsync is AWS's GraphQL option. It acts as a GraphQL server, which handles receiving the requests, stitching together the different information needed from a mutation or a query, and then returning that value to the client. It also works well with integrated AWS services such as CloudWatch for metrics and logs, and you can turn on things like X-Ray to do performance debugging. Appsync supports 5 different resolver types or data sources. In this case, HTTP, DynamoDB, Lambda, Aurora Serverless, and Elasticsearch. We found that we've only needed to use DynamoDB and Lambda for our system, and from talking to other people, that sounds like a common outcome. To give a bit more information about how this actually works, when you send a mutation or when you send a query to the backend, for this example, get my user query, where we want the first name, last name, and the messages that user has sent. Appsync uses VTL templates to know how to resolve that request. In this example, we're using a single table design, a Dynamo table. So we would fetch the collection using the information sent with get my user. We would then use the VTL template to manipulate that data to be in the correct structure to send back, and then Appsync will send that to the user. Alternatively, you can use nested resolvers. So in this case, we'd actually hit the Dynamo table twice, or multiple tables even. First hitting users to get the first name, last name, and any information needed by the messages resolver. And then the messages resolver would go and get all the messages for that user. You can see there's a new field now, next token. And that's because when you use Appsync's built-in resolvers, you can get pagination out of the box. So you might need the power of a single table design if you're working at that sort of scale, but it does lead to more complicated VTL, and you do lose some of these powerful features that Appsync can provide, such as pagination. And as you probably remember from earlier, a large part of this topic was upskilling the client. And so we found that DynamoDB is often one of the hardest parts of moving to a serverless first architecture. And so using multiple queries, while not the absolute most efficient, it's good enough and allows us to still focus on teaching them good DynamoDB practices without expecting them to understand everything from day one. And if it turns out that a query needs to be optimized in the future, there are options like using cache or rewriting the table to be single table design as the developer understands that concept more in the future. Appsync also works really well out of the box with Cognito. You will have seen that the query we've been looking at, get my user, doesn't take any arguments. That's because we have access to identity information in our resolvers. So for example, if we're using Cognito user pools in the VTL, we can look at the username or the claims and pass that to our queries. So users can only ever access their own information. This allows us to easily add access control for personalized information. But for further access control, it also works really well with Cognito Groups. So in our system, we want anyone to be able to send messages, so attendees or hosts. But we have a host user which also needs to be able to moderate messages. So for example, say an attendee sends something inappropriate, a host should be able to delete that message. So in this case, it's a one-liner. You put at AWS_auth, and you can specify which Cognito group can do that mutation. So in the first case, with send message, we're saying attendee or host can do this. But for delete message, we're only allowing hosts to delete messages. And so it's really powerful. You get a lot of access control out of the box with AWS, where if you were with AWS Appsync, where if you're using something like API Gateway, you'd have to write a lot of that yourself. Now, I've talked a lot about VTL, but haven't shown much examples. Thankfully, if you're not used to VTL, AWS provides a lot of templates that you can use out of the box. In this case, if you want to do a simple query, you can select simple query with pagination from the dropdown, and all you'd have to do is go through and update the expression ID and the expression values, and it would just work. It's very simple. We found that people are able to get working with this quite quickly. But we do find that there still are some sharp edges, some learning curves when first using VTL. So to accelerate getting comfortable, we found that test-driven development really makes that quite a bit easier. So we use three main libraries for this: Jest, Amplify Appsync Simulator, and Amplify Velocity Template. Theodore also has an internal package that we use behind the scenes to provide a few helper functions. This will hopefully be released quite soon under the name SLS Test Tools. But here is an example of a very simple test, just making sure that the arguments past the mutation make it into the Dynamo query correctly. For example, that the partition key is event hash and then the event argument that was passed in this case 1, and also making sure that the message passed in is the correct message. It looks like a very simple test, but it has caught some quite silly mistakes that we've done in the past when you're first getting used to VTL. A more interesting or novel example would be doing some error validation. So here we're saying that a user can't send a message with more than 2,000 characters. And if they do, we want to throw back an error to the front end that says cannot post over 2,000 characters. It's quite a simple test, and the VTL is quite small, but it's quite powerful. This is something that you would want to check works. But that's a quick overview of Appsync. Now, my talk mentions real-time updates in the title, and we're a good way through my talk, and I've not mentioned them yet. Thankfully, that's because we've secretly done all the setup we need. Mutations are the bulk of the work, and we just need to go back to our schema and add a few lines, and real-time updates are ready to go. So if we look at the schema, we need to go add a third high-level type or top-level type subscription. And then for any mutations that we want to have real-time updates for, we need to go add a subscription to our subscription type. So our example here is message sent, which will send an update to users anytime a send message mutation is received by Appsync. Subscriptions are WebSocket connections that notify users when a mutation has been resolved. You can see in this example as well that our subscription takes an argument. These arguments let you filter which mutations you notify the user of. In this case, we should only send users the messages for event chat rooms they're currently in. If you're in a chat room for a particular event, you wouldn't want messages from another event popping up. But other than that, this is all the backend code you actually need to write, and you have subscriptions working. It's a bit more complicated on the front end, but there are some very good libraries for that, and it's no more complicated than any other WebSocket implementation. We found using Apollo has worked quite well, but I know other people use Amplify with great success as well. There are a few gotchas for people that haven't used subscriptions before. The first one being that the users will only receive fields that the original mutation returned. To remember this, people often refer to subscriptions as being the result of someone else's mutation. I know there was a few times where we've tried to figure out why a field was null, and it turns out it's just because the original mutation wasn't sending those fields back. And the next gotcha is when applying filters to subscriptions, it's quite natural for people to assume that these apply to the arguments of the mutation. For example, when I was filtering the message sent subscription by event ID, the send message mutation needs to return that event field with that value that I filtered on for it to be received by the subscription. If I don't return event ID, it won't be fired. Or if it was a different event ID, even if that same event ID was in the arguments, then it wouldn't be received by that subscription either. But really, that's all you need to add for real-time updates as far as Appsync goes. It really is quite simple. The other part of this was high scale. So how does scale work with Appsync? I want to say quite well. So there are a few limits that you need to keep in mind, particularly that you can only have 1,000. There's a soft limit of 1,000 queries per second, but that is a soft limit. You can request AWS to increase that for you. There are some hard limits that are interesting here, such as a schema document can't be more than a megabyte. We've not got anywhere close to that, and we've not heard of too many people getting close to that either. But if you did, you could split that into multiple endpoints instead of just having a single GraphQL endpoint. Or if you were getting to that sort of scale, perhaps you would want to write something more custom. The other one is pipeline resolvers. I've not actually talked about pipeline resolvers yet. Basically, pipeline resolvers are where you can link up multiple requests for a single resolver, and these are limited to 10. But if you do need to do 10 distinct actions for a single resolver, then that's probably quite complicated, and you might want to look at using a Lambda for that resolver instead, as it'd be writing that in JavaScript would be a bit more expressive and it'd be easier to test, or TypeScript. And lastly, I just want to show our subscriptions actually scalable. So subscriptions are built on top of WebSockets, and AWS has done a demo where they've had 10 million concurrent users connected to a subscription at a time. And so I think we can safely say that it scales really well. If you do need to fine tune the scalability performance of a particular query or resolver, Appsync supports caching out of the box. So that, like I said, that can be either at the whole query level or for particular resolvers, but it will come at an extra cost. That extra cost might be cheaper than hitting the Dynamo table more though, so worth keeping in mind. And lastly, it's easy to say that it scales, but how does the whole price hold up? We'll add $4 per million queries quite well. That sounds a bit more expensive than API Gateway at first glance, but you've got to keep in mind you'll be doing less queries than you would be doing requests, because a query can contain the information of 3, 4, or even more requests in it. When you load a page, whatever information, you'd probably just grab all at once, and that would count as a single query. Lastly, our goal was to upscale the team as we went. So how did we find upscaling the team? Firstly, GraphQL is quite intuitive. People have found it really easy to pick up. There's a massive community around and lots of documentation. So if there's anything you are stuck with, someone's probably explained that concept in a way that you'll find really easy to understand, even if you just have to do a little bit of digging. Util was a little bit painful, but once you get used to it, it's really powerful and quite quick to develop with. And we do think that we have found that TDD is a really effective way of getting people to that point earlier. But as a worst case, you can always fall back on Lambda functions if you're doing something that you're not comfortable with ETL or is overly complicated. Although it is good to keep in mind that it does come with the extra cost of Lambda, both money-wise and also hitting the occasional cold start. And lastly, DynamoDB is where we find particularly experienced developers struggle the most. We often say they need to forget everything they know about databases. Thankfully, Appsync does make that a bit easier, but it is important to understand the underlying Dynamo tools that you're using. And so for that, I recommend Alex Debris' book to anyone that hasn't read it, the DynamoDB book. Otherwise, thanks for listening to my talk. I look forward to answering any questions at the live Q&A. If you want to access these slides, they're available on slides.com. Here's a QR code. Or if you'd like to work with us, either as a client or you want to join the team at Kyoto, you can scan the other QR code as well.